All right, we are going to spend a couple days talking about simplifying radicals. This might be something that you saw in junior high. We'll see. Either way, it's a bit of a review of when we did prime factorization. Does anybody remember doing that? Factor trees? Nobody remembers factor trees. Couple head nods. Okay, well, if not, let's warm up and make our factor trees. Now, our factor sheet, the pink sheet, could help us get started on these. In order to make a factor tree, we've got to split it into two factors. But what number can we never use? A 1. So we cannot use 1 and 81. We've got to use a different factor pair. What do you want to use? Ryan? 9 and 9. I like those. And we keep on breaking down these numbers until we cannot break them down anymore. So our 9s can both break down into what? 3 and 3. Can those 3s break down? No. So we are done making our factor tree. It just says make a factor tree. We don't have to worry about writing out the prime factorization or crossing anything off. They just want the tree. So let's move on to number 2 and break down 48. What could I break 48 into, Natalie? 6 and 8. Both of those can be broken down more. What will 6 break into? 2 and 3, and 8 breaks into 2 and 4. What's the only number up there I can still break down? 4. The 4 breaks into 2 and 2. That's not the only way to make a factor tree for either of those, but it's one way we can do it. All right, number 3 asks us to list the perfect squares up to 100. So let's start small and go in order. What's our first perfect square number? 2. Remember, perfect squares come from taking a number times itself. 64 is a perfect square number, but it's not where we want to start. Kian? 2 is not a perfect square number because you cannot take a number times itself and get a 2. Any other ideas? 4 is a pretty small one, but it's not the smallest one. So 4 would be 2 times 2, so we're getting smaller. 1. 1 is our first perfect square number. 1 times 1 equals 1. Jakeem gave us our next one. 2 times 2 is 4. What number do you think I want next?
8.
Not 8. 9. 3 times 3 is 9. After 9? 16. That would be 4 times 4. So my next one would be 25. For 5 times 5. What comes next? 36. Good. 6 times 6. After 36? 49 is 7 times 7. After 49? 64. Good. That's one that we'd gotten earlier. That's 8 times 8. After that, we would want 81 for 9 times 9. And after 81? 100, which is where we can stop. That's 10 times 10. Questions about how we come up with perfect square numbers? If you know your perfect square numbers, that will help you immensely with simplifying radicals. So I know it's just a warm-up. We don't usually think these are too terribly important, but I would maybe put a star by this one because knowing these numbers can be very useful for the next couple sections. All right. Let's get into our notes. For any non-negative, so non-negative meaning it's 0 or positive, real numbers a and b, the square root of a times b is equal to the square root of a times the square root of b. This goes in that box, the product property for radicals. So we've got an example at the bottom of that box, the square root of 50. Now if we were just to start our factor tree, just start it off, what's one factor pair for 50? I wouldn't recommend using a 1. If I were to start my factor tree, Houston, 2 and what? 2 and 25. So that would work. So I'm going to write this as the square root of 2 times 25. We all agree 2 times 25 is 50? So this property says that if I do that, if I split this up into a product or a multiplication problem, then I can split my radical over each number that's under there getting multiplied together. So this would be the same thing as the square root of 2 times the square root of 25. Now in some of the problems moving on, we'll simplify it more than that, but this just illustrates that property. We can take a number, write it as a multiplication problem, and then split our radical over the numbers or the factors. Questions before we move on? Okay. So we are going to simplify radicals 2 different ways. One way is going to be by using our factor tree method. Then the second way, we'll do the perfect square method. So our factor tree method, we just start off by making a factor tree for that number. So what could I split 120 into? Jamal? 2 and 60 will work. Okay, which of those can keep going? 60, what does 60 break into? 2 and 30, sure. What does 30 break into? 2 and 15. What about 15? 3 and 5. Now when we simplify radicals using the factor tree method, we are looking for pairs of numbers that are at the bottoms of our branches. So if you need to, kind of like we did when we did prime factorization, cross off any number that you broke down because you don't really care about those. We only care about numbers that did not get broken down. So what do we see a pair of up there? 2s. We got a pair of 2s. Doesn't really matter which pair of 2s you circle. You could circle these bottom 2. You could have circled this one with the other one. We're going to circle a pair of 2s. Do we have any other pairs up there? Okay, once we've used these, we can't reuse them. So there's no pairs out of 2, 3, 5. When we do this, any number that came from a pair, one number representing that group is going to come outside of the radical. So because I had a pair of 2s, I can write 1, 2 outside of the radical. And all the rest of the numbers that were left over go back inside of the radical. So 2 times 3 times 5. The part that gets a little confusing is that we had 2 2s here, but only one of them got to come out. It's like that group melded together, and now it's just a single 2 outside of the radical. Questions about that process? Our last step is to multiply things back together. So there's a 2 on the outside, there's nothing with it, but we can multiply 2 times 3 times 5 back together, and what would we get? 30. And that is how we would simplify that radical. So we would get 2 root 30. Questions, concerns about it? Okay, so that's one method of simplifying radicals. The other method is the perfect square method. So when you do the perfect square method, it helps if you know your perfect square numbers. So if you look at that list that we made of perfect square numbers from the warm-up number 3, which of those numbers can divide into 120? So if you look at that list we made on warm-up 3, 1, 4, 9, 16, that list from before, 4 can divide into 120. Do we all see that? Are we all okay with that? So we could rewrite this as the square root of 4 times, what would we have to multiply 4 by to make 120? 30. So this is using that product property from the box right above. We broke 120 into 4 times 30. And then we can break the radical over the multiplication problem. So the square root of 4 times the square root of 30. The reason we looked for a perfect square number is that we can take a square root of a perfect square number. What's the square root of 4? Heard a couple people say it, 2. So this becomes 2 times the square root of 30. You can put the multiplication dot in there if you want to, but you don't have to. And you'll see that we got the same answer either way. I think that the perfect square method can be quicker, but you have to really be confident in knowing your perfect square numbers and figuring out which one divides into your number under the radical. All right, which way do we want to go about simplifying these? Did we like the factor tree or did we like the perfect squares? You like the factor tree? Okay, the factor tree is a little bit easier to get started, I think. Just because if you have your factor sheet with you, you can easily find your starting factor pair. So what's our starting factor pair that we want to use for 48? Sure, we can use 2 and 24. Which one of those breaks down more? The 24 breaks into 2 and 12. 12 breaks into 2 and 6. 6 breaks into 2 and 3. Okay, so now we've got it broken down as much as we can. If you want to, go ahead and cross off all those numbers that got broken down so that we don't get distracted by them. And what are we looking for after we make our factor tree? Pairs. What do we have a pair of? 2s. What else? More 2s. So we have 2 pairs of 2s. Anything else? No. All right, so we write our radical down. What can I write outside of my radical? 2 and 2. 1, 2 for each pair, and those will get multiplied together. Anything that comes outside gets multiplied together. Anything that stays inside gets multiplied together. What's staying inside? 3. Anything else? No. So remember, we crossed off all those other numbers because we don't reuse them, inside or outside. We don't reuse them if we crossed them off. 2 times 2 is 4, so we end up with 4 root 3. Questions, concerns? If you preferred the perfect square way and you just didn't want to say it, this would be the square root of 16 times 3. That's a factor pair for 48. So if you have your pink factor sheet and you want to try to identify factor pairs for smaller numbers, like 48's on your factor sheet, and you know 16's a perfect square number, the square root of 16 times the square root of 3 would be 4 root 3. Same thing. Two different ways of doing the same problem. So you pick whichever way you want. 216, it might be easier to get started with a factor tree just because 216's not on our pink factor sheet. It doesn't go up that high. So what do we want to break 216 into? Now I'll give you a helpful hint. Anytime you have an even number, you know that it's got to be divisible by 2. So if you're not sure where to start and it's an even number, start with a 2. 216 divided by 2 would give me 108. If you're not sure where to get started with 108, it's also an even number, so we could also divide that by 2. 2 times what? 54. Now 54 is a small enough number that either you're familiar with it or you can look at your pink factor sheet. What do we want to break 54 into? 3 and 18. Sure, works for me. It's not our only option, but it's one that works. Which number can keep going? 18 breaks into 2 and 9. 9 breaks into 3 and 3. Anything else we can break down? No. Go ahead and cross off numbers that we broke down so that you don't get distracted by them. Now what are we doing? Looking for pairs. What do we have a pair of? You got a pair of 2s up here. What else? 3s. Anything else? No, nothing else. So we've got a pair of 2s, a pair of 3s. We got a couple numbers alone. Sometimes I like to underline my numbers that are alone so that I don't forget about them. All right. I'm going to do this one kind of off to the side here. We write our radical. Anything that had a pair gets written where? Outside. So what can I write outside? A 2 and a 3. Those are going to get multiplied together. What's going inside? A 2 and a 3, because the 2 was left over, a 3 was left over. And again, if it goes inside, they get multiplied back together. So what do I have on the outside? 2 times 3 is 6. What do I have inside? Another 6. So we have 6 square root 6. Questions, concerns? How are we feeling about simplifying these? One person feels good about it. A couple people might feel okay. All right, we got a big one on number 3. But it ends in a 0, so it's divisible by 10. That's another one to look for. 2 would work, but I like 10 on ones that end in a 0. 10 times what? 96. Which of those can keep going? Both of them. What will 10 break into? 2 and 5. 96. 4 and 24. Where do we want to keep working? 4 and 24. Which one do you want to do first? Okay. What will 24 break into? 2 and 12. Where do we want to keep working now? What breaks down? 2 and 6. What will it break into? 2 and 3. Are we done? No, we gotta go back up to that 4. That 4 breaks into 2 and 2. All right. Now, I still recommend that you cross off anything that you broke down just so that you don't try to go back to them. When we were doing factor trees for prime factorization, I had a lot of people that would put their 4s on their prime factorization list even though they broke it into 2s. So anything that we broke down, anything that's got little branches underneath of it, cross it off. Now with what's left, what am I looking for? Pairs. What do I have a pair of? 2s. Okay, I don't really care where you work. I'll just start over here. What else? 2s. I'll pull these ones from the middle. What else? 2s. Anything else? No. What's left over? Okay, the 5 and the 3. So remember, I kind of like to underline those so I don't forget about them. I don't lose them. That 5 can easily get lost in the middle there. I don't want to leave them behind. So I'll write my answer above. I've got my square root. What's going to be on the outside? How many 2s? 3 of them, because I had 3 pairs. 2 times 2 times 2. What's inside? 3 times 5. Good. So 2 times 2 times 2 is 8. And 3 times 5 is 15. Questions, concerns? We're sure? Okay, if you remember your prime factorization trees from before, this process is just adding a little bit of a different step on the end with the pairs. All right, number 4 is a little bit tricky getting started. Did anybody find something we could divide into this? 7 and what? 7 and 21? That'll work for me. All right, what number is going to keep going? 21 breaks into 3 and 7. Can anything keep going? No. So we cross off the ones we broke down. What are we looking for? Pair of 7s. Now these are not convenient to circle together because they're split up, but that's okay. We can still just create like a little loop-de-loop to circle that pair. What's left over? That 3. So what's my answer going to look like? 7 times the square root of 3. So now on this one, there's nothing to multiply together. One number came out, one number stayed inside, and then we're done. Short and simple. If there's a number outside already, we don't really do anything with it until the end. It's just going to stay out in the front, and we're just going to have to remember to bring it with us when we start writing our answer. So if you want, you can kind of set up your skeleton radical up at the top and just know that whatever else we bring outside is going to get multiplied to that 3 that's already out there. Does that make sense? All right, so we are focused on breaking down which number? 200. What can we break it into? 2 and 100. Now, we can be a little bit careful about what we break the 100 into. We could use 2 and 50. There's something I like a little bit more. 10 and 10. If we can break it into 2 of the same number, because it's a perfect square number, you do not have to keep breaking it down. Does that make sense? You can. You could break these both into 2 and 5 and 2 and 5, but then you're just going to be multiplying those 2s and 5s back together. So I know it kind of goes against the prime factorization that we talked about before, but if you find a perfect square number in your factor tree and you split it into a pair, you don't have to keep breaking them down. Does that make sense? If you don't recognize it and you were to do 2 and 50 and break it down that way, that's fine. You would get the same answer in the end. This is just a little bit of a shortcut if you can identify it. Okay, so if we stop at that pair, there's nothing else we have to break down. What's coming outside? Whoa. What's coming out? The 3's already out. Can we pull that 2 out?
Nah, never mind. 10.
No, that 2 doesn't have a friend. We didn't circle him. What did we circle? 10.
Yeah.
So some of you were saying 10 all along, and I appreciate that. But some of you seemed a little confused. What's staying inside? The 2, because he was all alone. He didn't have any friends. He's got to stay inside. Now to write our final answer, what do we still need to do? Multiply 10 times 3. 30 times the square root of 2. On 6, we've got that 10 that's going to stay outside. Somebody tell me what they broke 320 into. 8 and 40, I like that. That'll work. So, what did we break 40 into?
4 and 10.
Could do 4 and 10. What else could we do? 2 and 20. Anything else?
5 and 8.
5 and 8. Why do you think I like 5 and 8? Because I already have an 8. Okay, so you don't have to find these little shortcuts, but they might be useful. If you were to keep breaking down your 8s, you can. What are the 8s going to break into? 2 and 4. 4 breaks into 2 and 2. This 8 breaks down the same way. And then what do I end up circling? How many pairs of 2s? 3. 2s, 2s, 2s. What's going to happen with all those 2s? They're going to get multiplied back together, and 2 times 2 times 2 is 8. So when I saw that pair of 8s here, that's why I liked that, because if I see a pair of numbers, I can circle that pair and stop breaking them down. Now, if you kept going and you got all your 2s, that's fine. That totally works, but we just multiply them all back together and we end up getting an 8 out of them anyway. And what's staying inside? Anything with the 5? No, the 5 was all of them. Okay, remember, anything that got broken down, we cross off so that we don't use it. So if we broke down all those 8s, we'd cross them off. 2 times 2 times 2, we already said is 8, but that still has to get multiplied to the 10. That gives us 80 root 5. Anybody get 80 root 5?
No, that's not good.
What do we get?
I broke mine down as like 320 and 32.
Okay, let's talk about the 10 and 32 way. We broke it down into 10 and 32. What'd you break your 10 into? What'd you break your 32 into? 16 breaks into. The 4s break into. Okay. So then we start looking for our pairs. So it's easy to see the pairs of 2s down here, right, from the 4s. But where else do we have a pair of 2s? Kind of in that second line here. Even though they're not right next to each other, we can circle those 2s. So we still end up with 3 pairs of 2s, and what's alone? A 5. Anybody else need me to check how they broke it down? Deshaun? You used what? 4 and 80. Okay. 4 and 80. The 4 breaks into. The 80 breaks into. That's where you went around. That's 60. So 80, we could do like 2 and 40. 2 and 20. 2 and 10, 2 and 5. It's going to be the same thing. 3 pairs of 2s. Questions, concerns? Okay, we might get to those last 2 as a warm-up tomorrow, but I want time to pass out your homework.
Yes.